Good day, I'm Dr. T and welcome to my whiteboard. Okay, so I'd like to talk about different types of reactions today. And we have generally four major categories of reactions that we like to think about, although we generally talk about more specific types. But first, those kind of four major categories of reactions. The first up on the board is what we call a combination reaction. This is where you have two components, in this case carbon and oxygen, that are combining together to form one chemical. So I'm going from two or more chemicals into one chemical. A decomposition reaction is literally the reverse. I'm going from one chemical, in this case mercuric oxide, and I'm going to two different chemicals, in this case mercury and oxygen. The third type that we often talk about is known as a single replacement reaction. In this case, I've got an ionic compound and an element, and I'm going to be swapping the cation of the ionic compound for the element. So, cupric chloride and iron will react to form ferric chloride and copper metal. The last of the major types is what we call a double replacement or double displacement. In either case, the term replacement or displacement are interchangeable. It's kind of an older style versus a newer style of speaking. Generally, newer textbooks will call it replacement. Now, in the double replacement or double displacement, if you're old like me, we'll have an ionic compound, a second ionic compound, and they're basically going to trade cations and anions. So I have plumbous nitrate or lead-2 nitrate, I have potassium iodide, and I'm going to get lead-2 iodide and potassium nitrate. I'm simply going to trade partners. So there's our generally broad category of reactions. One of the major subcategories of chemical reactions that as chemists we like to talk about is that of the redox reaction. And in order to understand what's going on, it's actually useful to go back to the history of why we call them redox. And this goes back to metallurgy and two different types of reactions that metallurgists would do. And of course, as chemists, we have adapted their terminology, given it our own twist, and have taken it as our own. First is what we call reduction. In reduction, you are starting out with the metal's ore. Metals, for the most part, apart from, say, silver, gold, and to a lesser degree copper, are available not as a metal, but as an ore, as some kind of ionic compound. Once again, sometimes you do get a nugget, and it's usually of your coinage metals. Now, when you have an ore, it's not particularly useful by itself. You need to smelt it. And the process of smelting is also referred to as reduction. You're reducing the amount of material you have. So if my ore is magnetite, not necessarily the most common ore, but simple for our example, then I have iron, or 3 irons into 4 oxygens paired together. It's both iron 3 and iron 2 in that particular formula. So as chemists, we just borrow the geologist term magnetite. Okay, that's going to be reacting with carbon. There's going to be some oxygen involved in order to get the heat up, and this is actually a fairly streamlined version of this reaction, but I am removing the details for better clarity. Okay, we're going to be reacting with carbon, and in the process we're going to get iron metal and then carbon dioxide. So this is basically a single replacement reaction. Now, when we look at this, it's interesting to see what is going on. If I look at the number of electrons around this carbon, things are starting to change around. Effectively, although through a bit of horse trading, electrons are traveling from the carbon to the iron. So as chemists, whenever we see a reaction in which electrons are being given to an element, so they're going from somebody going to another element, we call this reduction, which gets abbreviated as red. Now, you're probably thinking something fairly straightforward. Hey, wait a minute, didn't the carbon give up its electrons? So it's got to be involved in this somehow too. And to think about this, we like to go back to the metallurgists for another reaction that they would look at. This is a classic reaction. It's usually an undesirable one, but if you have a lot of metals, and iron, of course, is the classic case, if you have those metals and in the presence of oxygen or other chemicals that particularly like oxygen or like electrons, they will lose their electrons. So in this case, the iron is losing its electrons and it's becoming iron 3 oxide, or red rust in this case, hematite if you're a geologist. The process of losing electrons we started calling oxidation, or for short, ox. Now, if you're following along, you should quickly notice that with respect to the iron, this reaction is reduction, but with respect to the carbon, this reaction is oxidation. Likewise, this reaction with respect to the iron is oxidation, but with respect to the oxygen, it is reduction. All reactions that are either oxidation or reduction are actually both. Electrons don't magically appear, they have to come from somewhere, and if they leave, they don't magically disappear, they go someplace else. So, this reaction is both reduction and oxidation, so we call it redox. I know it's spelled like red ox, but it's pronounced redox. And likewise, this one is, while oxidation, also reduction. So, a redox reaction as well. A little bit of terminology here. For starters, we can say that the iron is being reduced in this particular reaction, or that the copper is being oxidized. And by copper, I mean carbon. Down here, we can say that iron is being oxidized, or that the oxygen is being reduced. Fairly straightforward. We can change things up, though. Up here, we can say that the carbon is what we call the reducing agent. The reducing agent is the chemical that is causing the other chemical to be reduced. So the carbon, I know, C, right? The carbon is causing this iron to be reduced, so we call the carbon the reducing agent. Sometimes in a reaction, I need a chemical that will cause something to happen, so I look at chemicals that can act as reducing agents. Likewise, the oxygen is causing the iron to be oxidized. So we call that an oxidizing agent. Whoever is being reduced is the oxidizing agent, and whoever is being oxidized is the reducing agent. It's really a frame of reference shift, depending if we're talking about the individual chemical or about the other chemical involved in the reaction. Although, with all frame of reference shifts, you do have to keep in mind which way you're going, and they can be a little bit confusing if you're not paying close attention. One interesting feature of chemical reactions is that quite often they are reversible, and we denote that by a two-ended arrow, kind of as I have shown here. This is what we call an equilibrium reaction. In this case, my reactants, hydrogen and nitrogen, can react to form ammonia, NH3, but ammonia can, at the exact same time, convert itself back into H2 and N2. At a certain point, the amount of production of ammonia will cancel out with the amount of degradation of ammonia, and we'll reach what's known as equilibrium. Most reactions are like this, and in reality you can imagine that all reactions are technically reversible, although reversibility is kind of a relative scale. You can imagine jumping off of a curb, you could just as easily jump back up. You could jump off a cliff, and in theory you could jump back up if you had a rocket pack, or a rocket or something, but you're not going to. So for those reactions that are effectively one-way, there's always a reason why they are a one-way reaction. When they are a one-way reaction, we're going to use a one-way arrow, an arrow that points in one direction. For this course, we're typically going to be focusing on these one-way. Once we progress further and move on a bit, usually in the second semester, then we'll jump into two-way reactions a bit more. But let's keep things simple and go and stay with one-way. That said, one-way reactions always are one-way for a reason, and there's a couple of good reasons why they might be one-way reactions. The first is what we call a precipitation reaction, often abbreviated PPT, although you do have to be careful with PPT as it's the abbreviation for several things. In this case, we have a reaction we have already shown before. You have aqueous lead to nitrate reacting with aqueous potassium iodide. And these are going to form aqueous potassium nitrate, but also the precipitate led to iodide. This reaction is taking place in water. It's an aqueous environment. And anything that would remove a chemical from that aqueous environment would prevent it from going in reverse of the reaction. You can't go backwards if you have left. And even though it's not outside of our container, it will sink to the bottom. Lead to iodide is insoluble in water. It forms a tight lattice that doesn't like to break apart in water and will sink to the bottom. It looks like it's snowing in some cases, hence the name precipitation. Now we can go for a couple other approaches. Over here we have an acid-base reaction. Acids are going to be any compound that increases the amount of H+ in an aqueous solution. The simplest way, of course, is to simply provide the H+. Although there are some compounds that react with the water in order to generate H+ in the aqueous solution. A base is effectively the opposite. There's a couple of different definitions. One would be any compound that reduces the amount of H+ within your solution. Another is any compound that generates OH-, or would have a hydroxide function or hydroxide group as its anion. So sodium hydroxide here would be a classic case. When you have a hydroxide and a hydrogen or an H+ reacting, they will react to form water. Now, water is what we call a weak electrolyte. It doesn't really want to go back and become an H+ and an OH-, and because of this, the reaction is mostly one way. Depending on the acid and base involved, this can be a one-way acid-base reaction, although there are definitely acids and bases that are two-way, in reality the majority. It all falls down to how much the what we call the conjugate acid or conjugate base, what's left over, so the Cl would become the conjugate base, it's left over from the acid, and the Na would be the conjugate acid, what's left over from the base. How much those want to reacquire what they had originally. In this particular case, we call these strong acids and strong bases because they don't. It's a one-way reaction. Weak acids, weak bases will be in equilibrium. And we'll deal with those later. Now, another way you can leave the party, leave the aqueous environment, is a gas-forming reaction. So in this case, we have the reaction of hydrogen peroxide. This is using a catalyst called catalase. This is an enzyme generated by cells. And if you treat a wound with hydrogen peroxide, which is generally no longer recommended since it does a little too much collateral damage, but if you do, you'll notice how the wound bubbles. That is because the cells contain catalase and they're trying to get rid of the hydrogen peroxide. This enzyme causes a reaction where hydrogen peroxide is degraded into water, which once again, is a liquid. It's not dissolved in itself, it just is, and would prefer not to do the reaction, but also oxygen gas, which is simply going to leave. It's going to bubble off, or what we call evolve. And thus, it's no longer in the reaction, and therefore can't go back. The last one I want to point out is that of the redox reaction, and we've already covered redox reactions. But I'd like to bring up another one. This is actually called the Thermite reaction. It's used for several functions, including welding railroad rails together. Trying to say that 10 times fast. In this case, we have iron oxide. This is going to be our oxidizing agent. Our reducing agent is going to be aluminum metal. These are both finely granulated, so a very fine powder. Given enough heat to get them kick-started, and then you will get iron. And in reality, this is liquid iron because it's ludicrously hot. And you will get either solid or liquid aluminum. Never really looked into which one you get, but you're going to get some aluminum oxide. This process, the aluminum is less interested in the electrons than the iron is. So once the electrons move to the iron isn't willing to give them up and back to the aluminum. And thus this reaction becomes a one-way reaction. Now let's talk about identifying redox reactions. In the first case, which we're involving some metals, is fairly straightforward. We want to see if electrons have moved. Now if I look at this, I can immediately say that my initial iron is metallic. It's not charged, it's by itself. So this has a charge of 0. The copper it is paired with 2 chlorines. Since the chloride anion has a -1 charge, I know that the copper has a +2 charge. Now, in the products, we have a slightly different story. The copper is all by itself, so this has a 0 charge. It's the metallic copper. The iron, though, it's with 3 chlorides, so it must be a +3 charge. And this is the telltale sign that I have a redox reaction. My charges have changed. The iron has gone up. It's clearly been oxidized. It's lost electrons. The copper, on the other hand, is gone down. It has been reduced. The charge is now lower. And thus, I have a redox reaction, and I know who has done what. The iron has been oxidized, so it's the reducing agent, and the copper has been reduced, therefore it's also the oxidizing agent. However, when we're not dealing with ionic compounds, things get a little bit more tricky. So in this case, I have what's known as a combustion reaction. In combustion reactions, they're a specialized form of a redox reaction, and depending on quite where you look for the definition, they will either be limited to or implied, but not necessarily limited, to reactions that are involving molecular oxygen, so O2, as well as a hydrocarbon fuel, something that contains carbon, hydrogen, maybe some oxygen in for fun. So a combustion reaction is going to be a redox reaction, but it's dealing with molecules, not ions, so it's a little harder to identify. In this case, we need to use what's known as oxidation numbers, and, well, it's actually basically what I just did up here. Certain atoms will almost always have the same oxidation number, the same number of electrons that if this was an ionic compound, even though it's not an ionic compound, but let's say it was an ionic compound, this is what they would have. For hydrogen, if it's attached to a nonmetal, it's always going to be +1. Now, if it was attached to a metal, we would say it was -1. Hydrogen gets a little bit interesting depending on where it's hooked to. But that's a nonmetal, it's +1. So it would be behaving like it's a cation, even though it's not. It's not having its electrons stolen, it's sharing, actually quite equally with the carbon. But we're going to pretend it's a cation. Oxygen is its elemental form. Whenever you're in your elemental form, you assume you have an oxidation number of 0. You're sharing equally with, yourself. Now, the quick question is, what is carbon? Carbon can be quite a few different things. It can be in its elemental form, and thus 0, but it's not. But wait, we know what it's attached to. We know that it's attached to 4 hydrogens. Each one of those is a +1. The sum of your oxidation numbers always equals your charge. If I'm a neutral molecule, I have no charge, so the sum of my oxidation numbers is 0. So, what +1 + 1 + 1 plus another 1 gives me 0? Must be -4. So the carbon is -4. Okay, I've assigned my oxidation numbers, very much like I did up here. Of course, I forgot to do the chlorine on top, so yay. Your halogens are basically always -1, although they do vary when oxygen's involved. And of course, that's actually an anion, not just a neutral covalent compound. So, yay. Now, let's go over to this side. And this is going to help us show that, hey, this really is a redox reaction. For starters, oxygen is basically going to be -2 unless one of 2 conditions are met. First, that it's elemental oxygen, O2. So, that guy. Yeah, that's CO2. The second condition is if it's what we call a peroxide. This is an oxygen directly hooked to another oxygen. Not a particularly common thing, generally rather unstable, and the name of the compound will always have the word peroxide in its name. So you can basically assume, unless it's explicitly stated, that it's not a peroxide. If it was a peroxide, it would have a charge of -1. But it's not. And all other cases, oxygen will have a charge of -2. Just as if it was an anion. So this is a -2, that is a -2. Hydrogen, as I mentioned before, if it's hooked to a non-metal, it's going to be +1. And look, the water works. I have +1 times 2 of them. added to -2, and together that is 0. 1 plus 1 minus 2 is nothing. Yay! But wait, the CO2. In that case, I'm going to have to figure out what the carbon is. Now, I have 2 times -2, so that's -4. So what minus 4 is 0? Plus 4. And now I know my players. The hydrogen hasn't changed its oxidation number. It's simply moved around. It's not a reducing or oxidizing agent. Its electrons, well, it's just moving. The carbon, however, that has gone from -4 all the way to +4. It's been heavily oxidized. In a combustion reaction, your fuel is going to get oxidized. Or we could say it's a reducing agent. We quite often will call it a reduced fuel. The oxygen, that went from 0 to -2. It was reduced. Or we could say it's the oxidizing agent. The telltale sign, you know, oxidizing agent is actually named for the oxygen since it's such a good oxidizing agent. Although there are rare exceptions where oxygen is not the oxidizing agent. So, you know, don't always assume if you see oxygen, it is the oxidizing agent, although it almost certainly is, usually. Okay, I'd like to talk about 2 more ways to classify reactions. The first are some reactions will give off heat or give off energy, such as this combustion reaction up here. In fact, this is why we typically use this. This is natural gas over here, and hey, burning it, it's energy to heat your hot water or your stove or your house or whatever else. Also a great way of making electricity by burning it and turning a turbine. This is called an exothermic reaction because it's going to give off heat. And heat usually isn't written as a product, even though you really can think of it as a product. Even though, once again, we don't usually call it a product since it's not a material substance. It's energy, so it's not matter. Of course, the opposite of an exothermic would be an endothermic reaction. One where heat, as well as the other reactants, go together. So I'm going to have heat not really as a reactant, but once again I can think of it as a reactant. This is actually vinegar and washing soda in this case. Baking soda, it would have an extra hydrogen here and only one of these guys over here. That said, we've got this reaction, and if you do a vinegar baking soda or more extreme vinegar and washing soda, it's going to actually get colder because it's going to take heat in during the reaction. So it's going to react, it's going to form sodium acetate, some carbon dioxide, and some water. And yay! Thank you, and have a wonderful day.